So far we've looked at and defined what a vector is. So a vector has magnitude, which is length, and direction. And now we're going to look at some applications of using vectors. So in front of us, we have an example where an airplane travels on a bearing of 100 degrees at an airspeed of 190 miles per hour, while a wind is blowing 48 miles per hour from a 220 degrees. We want to find the ground speed of the airplane and the direction of its course over the ground. So first thing that we want to do is we want to create our vectors. So let's write our vectors. Recall, if we're starting at a bearing of 100 degrees, we're starting at that north line and we're going clockwise. So I'm going to go clockwise of 100 degrees, starting at the north line. And so we have a vector that looks like this. And the length here is its speed, which is 190. Miles per hour. If I look at the wind blowing, the wind is blowing from 220 degrees. So looking at a bearing, starting at the north line, we're going to go 220 degrees. So here is 180. So 180 plus 40 more degrees. This is going to be, so it's coming from, so it's going to go in the opposite direction. So it's going to be pointing upwards here. And it's 48 miles per hour. So this length of this vector is 48. So I know that this angle in here between the north and this vector, this is, well, it's 40 degrees down here. So congruently, this is 40 degrees. So let's look at this coming 40 degrees off of where our airplane is. And then we have this vector of our wind blowing 48. So if this is right here, 40 degrees, and the whole thing is 100 degrees, I know that 100 minus 40 is going to give me this angle inside between these two vectors. And so this is 60 degrees. I want to make my resultant vector. So summing these two vectors, I can make this parallelogram. So off of my terminal point of my airplane vector, I'm going up 48. And then, or going from the terminal point of my wind vector, I can make my airplane vector. And then the resultant is going to start here at the origin and it's going to come here. So it's going to look like this in here. So this will give me the course right here when I just drew in green of this line that was the diagonal of this parallelogram. That is going to be my course, and I can find out what my length is of that, the magnitude, which would give me the ground speed. Because we had this parallelogram in here and we knew some angles, let me just draw the parallelogram really quickly. So we saw that this was 60 degrees in here, which means that this angle over here is 60 degrees. So I know that when I sum all four of my angles, this is going to be 360 degrees. So I have 120 degrees. These angles in here are congruent. Call it alpha for now. So I know that 360 degrees should equal the sum of all my angles. So 60 degrees plus 60 degrees plus alpha, which is 2 alpha. So let's solve for alpha. So I have 360 degrees is equal to 120 degrees plus 2 alpha. Let's subtract 120 degrees on both sides. So that gives me 240 degrees is equal to 2 alpha. Dividing both sides by 2, I get that alpha is equal to 120 degrees. So I know this angle in here is 120 degrees. So I want to find this length of my resultant vector. And so notice that I have an angle sandwiched in between two known sides. And so I want to use, and here I can use law of cosines. Okay, so let's call this vector, this resultant vector, what we're trying to find, which is the ground speed. So I know that the magnitude of V, quantity squared, this is equal to the sum, so squaring this each side that is sandwiching it, so 190 squared plus 48 squared minus 2 times the one side 190 times the other side 48 cosine of the angle sandwiching it, which is 120 degrees. So if I plug this into the calculator and I look at 190 squared plus 48 squared minus 2 times 190 times 48 times cosine of 120, we get this is approximately 47,254. So this is the magnitude of V quantity squared. So if we took the square root of both sides, that we get the magnitude of V is equal to 218. So it's telling me that we are going 218 miles per hour is the ground speed. And so now I want to look at my course. And so I need to figure out what an angle is. So if I could find this angle in here, theta, then I can take that 100 degrees minus my theta to get me my course. And so notice that I have theta. I have the opposite side of the angle that I'm trying to find. And we just found that that resultant vector was 218. And so we can use the law of sines here. So let's use the law of sines. So using the law of sines, and I'm trying to find an angle. So I'm going to do sine of theta all over the side opposite of theta, which is 48 in my case, is equal to sine of 120 degrees all over the side across from 120 degrees, which we found to be 218. So if I multiply both sides by 48, I get sine theta is equal to 48 times sine of 120 degrees all over 218. So theta is going to equal to sine inverse of this 48 times sine of 120 all over 218. So if we plug that into the calculator, we should get that theta is approximately 11 degrees. So my direction, I'm going to look at that 100 degrees minus that 11 degrees. So my direction of the plane Well, 100 minus 100 degrees minus 11 degrees is 89 degrees. Or has a bearing of 189 degrees. So let's look at another example. So our next example says a vector W has a magnitude of 130 and is inclined 40 degrees with the horizontal. Find the vector's horizontal component and the vertical component. So let's draw what we have here. So we have our vector W, but we're going to go from the horizontal, we're going to go up 40 degrees. That gives us our vector W. It has a length here, it tells me of 130. And I want to find this horizontal component here. And I want to find this vertical component here. So let's call this vector U for the horizontal, V for the vertical. So I have a right triangle. So if I want to find U, I know that I have the hypotenuse, I have an angle, and that U is adjacent. So that would tell me that I want to use cosine. So cosine of 40 degrees is equal to the adjacent, which is the magnitude of our vector U, all over the hypotenuse, which is the magnitude of W, which we were given was 130. So looking at this, we can multiply both sides by 130. And so we get the magnitude of our vector U is equal to 130 times cosine of 40 degrees. So looking at this, plugging it into our calculator, we get this is approximately 100. So that is our horizontal component of our vector W. So looking at the magnitude of our vector V, this is equal to, so from 40 degrees, that is our opposite side, and we want our adjacent side. So that tells me to use sine. So actually, let's do that. So sine of 40 degrees is equal to the opposite. So that's the magnitude of V divided by the hypotenuse, which is the magnitude of W, which we were given was 130. So our magnitude of V, can multiply both sides by 130 in the equation we had above. So we have 130 sine of 100, not 100, 40 degrees. So this gives us approximately 84. So our horizontal component of W is approximately 100 to the right, and the vertical component of W is 84 up. So there's a couple examples of vectors.